To move on to more advanced work, we need the advanced level. So I'll just show you how to get there. If you go to View, Preferences, you can switch levels at General, there we are, Standard and Advanced. While you're at it, you also notice there's a convention for inequalities, which a lot of people get very concerned about. I prefer to shade the reject region so it leaves clear the points that agree with all the inequalities, but some people prefer the other. That's where it's done. Okay, advanced, and over we go. So it doesn't look that different, but there are several options which are not present in the standard level. For example, degrees and radians. There's more zoom options as well down here, but otherwise it's much the same, except of course the right-click menus include all the calculus options. So let's start with a new page, and once we start talking about calculus, let's talk about our old friend y equals x squared. Let's move that down to there. Let's have equal aspect, because you notice that's not on by default, but it's pretty important when we're talking about the gradient, so I'm going to put it on now. I'm going to put a point here and just move it up to there, and a point here at here and move it down. I want to have a look at the gradient as measured by the chord from here to here, so let's do right click, gradient, there it is. This of course I can move around. Quite useful I think also at this point to put on a tangent, because the gradient of the tangent is the ultimate measure of how steep a curve is, whereas the gradient of a chord is not, unless the chord gets so close that you can't tell the difference. And that I think is something we definitely want to look at. So if we select this point and double click down here, you will get the gradient marked up here. So we can use the arrow keys to make it go smaller. Notice the arrow keys don't work at the moment because I moved this around, which is a window. Just get the focus back to the main window and all will be well. Now we can zoom. The advantage of using the arrow keys here is that you can leave the zoom selected and keep going. And of course local straightness is kicking in. And we've got the idea of, basically if you look up here, the gradient is 2.003, change in y is 0.006, change in x 0.003. There could be a million zeros here and a million zeros here, and the answer would still be 2. So this idea that you've got the division of two numbers, both of which are tending to 0, producing a finite answer of 2. So that's quite nice, and then we'll have a look at the gradient properly in a minute. Just delete that. Let's put another point on here, wait for the back arrow, there it goes, and right click, let's do a tangent. So we can start building up what the first derivative of this graph is. So clearly it's 0 at this point. As we move it along, so we've already discovered that the gradient at this point is 2, 1 along and 2 up. Equal aspect is probably a good idea once again. And so that's 2. And if we keep going, the gradient up here is 1 along and 1, 2, 3, 4 up, so it actually is there as well. And if we go in here, there are always people who think that the gradient is going to be up here, but it's not, of course. It's now going negative, and if we go to this point here, 1 along and 2 down, and so on. So these clearly are in a straight line. So it's quite nice to introduce you now to this feature here, which is the gradient function. If you've got slow plot on, this will do automatically what I've just been doing manually. So let's have a look and see. And here it is, gobbling up all those brown splotches once again. It's a very good technique. So what's the equation of this line? Hopefully it's not too long since we've done straight line equations. And the answer, of course, is that it's a straight line with a gradient of 2, the one that we've met in earlier lessons. So y equals 2x, that's correct. So that's quite a nice way of looking at the introduction to differentiation. Let's put on a slightly more complicated graph now. Let's do y equals x cubed, xxx, minus 3x minus 1. Now that's going to be cubic, so we've got time to stop and think about it. So what sort of a graph is this? X cubed, well, x cubed goes like that, and minus 3x is like that, so it's going to pull it up here, pull it down here, and then the minus 1 means it definitely goes through here, and we know that it's this way up and this way up, so it's something like that. But that's the sort of thought process that's really useful to go through before something draws. Very good. Okay, edit, select all scribbles and delete. Now again, once again, let's put a point on here and right click a tangent. So we can see that the gradient is 0 at this point. As the gradient comes along here, now just look at the value of the gradient as it goes along here. It's never going to get more steep than it does there. So this is the steepest it gets. It's also the point where the tangent comes in one side and out the other. And that, of course, is called the point of inflection. So that's the most steep it gets. It's 1 along and 3 down, which is -3. And the next 0 is here. So we're looking at a parabola like that. And now let's do it formally. It's always good to do these things by hand first. And it stops at all the key moments. There's our minimum. I'm just going to edit, select all scribbles. Now that point is selected as well, so if I delete, it's going to delete the tangent. Tidies up nicely. Right, what about the gradient of the gradient? Well, if we do this again, this is now the current object, so I'm going to do it again, and you'll see that you get the gradient of the gradient. And that's going to be a straight line, of course, because if you differentiate this once, you get 3x squared minus 3. Differentiate it again, you're going to get 6x. Let's see what we do. It's just, is it 6x? Let's go and have a look. Drag. Yep, 6x, there it goes. So a nice way of introducing first and second derivatives and points of inflection. Trigonometry is done really nicely, especially now we have the degrees radians switch. So let's right click and enter an equation. Let's do y equals sine x. And you get that, and these scales are not really appropriate, but the red tick takes care of it beautifully. Watch this. Because we're in radians, it goes minus pi by 2 to 2 pi. But if we go into degrees, it looks a bit silly, which it would do. It's only pi by 2 is only 3 or so, not even that. And we do the red tick now, minus 90 to 360. So let's consider y equals sine squared x and see if we can puzzle that one out. What does it look like? Well, everything here is being squared. So 0 squared is 0, 1 squared is 1, 0 squared is 0, but minus 1 squared is plus 1. So it goes like that. And here, now, this is 1 over root 2. If you square that, you get a half. So this is going smaller. So we go up and down, up and down, and up and down. So it's looking like something which has double the frequency. It has its maximum on the y-axis, therefore it's more likely to be a cosine than a sine. So let's start exploring this and do y equals minus cos 2x. Well, it's certainly the right shape and the right frequency. It's just not. It's just too wide. It's got too big an amplitude. So double click on that and stick a half in there. That's better. All we've got to do now is shunt it up by a half. So double click down here and put a half in. And we're done. So let's just enter y equals sine squared x and see if we do indeed get that. Y equals sine squared x. And there it is. That's no proof that these two are equivalent, but it's a nice visualization. Put that down there, and right click, let's enter an equation, and I'm sure we've had it before, y equals x squared, there it is. and as before we're going to put a couple of points on, one here and one here. And right click, I'm going to find the area just on the bottom there. Now the various options here to do rectangles above and below, and trapezium rule, Simpson's rule, and 5 divisions. I'm going to do rectangles below 5 divisions. Try to visualize it first. 1, 2, 3, 4, 5. So it's going to be 5 divisions. That's going to be an underestimate for certain. And this is of course a variable area. So what is that area? Well, we've got the answer down here. It's double click 2.04. So we've got 2.04. We could also put it on in this form. Now the integral of x squared from 1 to 2 is dx 1/3 x cubed, top limit, and the answer is 2.3 recurring. Now that's clearly less than that. We'll obviously look at those holes. Okay, so I'm going to double click on this, click, and maybe suggest we put in 6. It would be much better though if we animated this rather than doing it that way. So select the area and only the area. If you select a point as well, the animation controller will give you the chance to move the point, which is not what we want. So deselect that and select just the area and animate. Right, ask another question. If the divisions go from 5 to 6, so there's more of these, is this number going to go up or down? Up. Okay, make sure they get the answer before you press the button. So as we keep doing these, the answer is going to get higher and higher and higher until eventually we get very close, don't we? So let's put in, say, 500 of these. 2.33. Well, there's one thing I haven't mentioned yet, which is the sig fig. It's set to 4 at the moment. So if we page settings and bump this up to say 10 sig fig, you can see that there's a long way to go. However, this is the point where dynamic software really comes into its own, because we can zoom. Watch this. I'm going to zoom on here now. 1, 2, 3, 4, 5. Now only after 6 zooms we get this situation again. So we've still got an underestimate, but still going to be a long way to get there. And of course it took the genius of Newton to go all the way to infinity. However, some bright student might say, well, supposing you put a trapezium in here instead, that would be pretty good, wouldn't it? So yes, let's do that. Double click. Let's do a trapezium rule and OK. Not bad. Is this going to be an overestimate or an underestimate? You might take the opportunity to cover that up, because that's giving the answer away. The answer is just over, but why? Let's have a look. Let's zoom in, and obviously thinking of the curvature, trapezium is definitely cutting the corner. And there it comes. So that's really nice. Now it'd be quite nice to do all this in 3D and have a look at the volume revolution of an area about an axis. So when you introduce 3D, lots of things you might do to start with. Just the idea of where is a point in 3D is quite useful. You know, what are the coordinates of that point? Well, you can't really tell because you don't know where it is. But what you could do is put a point on, right click, enter coordinates at say 1 tab 2 tab 3 and see where it is. Well, it's going to be 1 along the x, 2 along the y, and 3 up the z, so it's up here. So just get some idea of how 3D works is, I think, pretty important. The right click menu gives you a lot of things that you might expect, you know, the central equations, points, the vector equation of a straight line, the vector equation of a plane, just putting a shape on. So let's put an equation in. Let's do a slightly unusual one. We're going to put r equals z. Now r equals z turns out to be the polar equation of a cone. There it is, beautiful. Now if we want to put a plane in here, let's do the 3D equivalent of y equals mx plus c, and we're going to call it z equals mx plus c. M and c will both be 1, and what we get is a straight line. If you imagine that in 2D, that would be like that. But in 3D, it's a beautiful cross-section of a cone producing a nice parabola. The constant controller kicks in now, and what happens, we're not interested in changing C, but M definitely. If we make M steeper, it's going to start bumping into the bottom here, isn't it? Make M steeper, there it is, so we get our hyperbolas. Going the other way, we get ellipse, and then eventually we get the circle at M equals 0. And if you want to, you can zoom in. A nice trick with 3D is to press the control key and just pull down, and the camera goes roaring in. Don't leave control down though, because it causes a lot of troubles. So, new 2D page, have a quick look at areas now. Right click, let's enter an equation. Y equals, let's do x brackets 3 minus x. Now what this is, looks like a train tunnel on a train set, because there's no z here, is that? So if there's no z, it means for all z you get that equation. So I'm going to double click on this and invoke the option to plot as a 2D. There it goes. Right, now this time I'm going to select, and instead of putting 2 points, instead of this time I'm going to select the curve, and I could find the area straight off by just putting points in, but I'm going to enter a point on the graph, and let's do x equals a. What will that do? A is 1, so it's going to be about there. Perfect. Right, now I'm going to select this and enter a point on the graph again, this time at a plus 0.2. 1.1's a bit close. Perfect. Okay, control and drag. So now I want to select those two and right click, find the area. This time I only want one division, and I want rectangle below. That's perfect. So that's my element of area. There it is. And I want a line, so I enter an equation and do y equals minus 1, and I want to plot it as a 2D, otherwise it will be a plane. Perfect. If I select this area and this line and right click, find the volume, slow plot is on, which is great, so it's going to go around slowly, and my element of volume is going to be a washer. What would happen if I change this line from y equals minus 1 to x equals minus 1? Okay, so this and this, the element of volume now is a cylinder that goes round, and right click, let's have a look, find the volume, and round we go. Now if I double click on this area and give it say 10 divisions instead, and then change this to 0 and change this to 3, I've now got an approximation of the total area, and double click on that. You can see that I could change anything, but select that and select this, and round we go. Find the volume, okay, and we could double click on this and edit the area settings to Simpson's rule, which is really nice. So a nice way of illustrating volumes, and that concludes this short look at some of the advanced topics.